All right, let's dive into the invisible world of thermal energy. You know, the energy that makes some things feel hot and others feel cold. And we're going to kick things off with a classic campfire mystery.
So, picture this. You're hanging out by a campfire. You've got a metal poker, and after just a minute, that handle is way too hot to touch. But then you can hold a wooden stick right in the flames to get that perfectly golden brown marshmallow. What's the deal with that? It seems simple, but the answer? Well, it unlocks the secrets of how energy moves all around us.
To solve our campfire case, we've got to understand what's really going on in that fire. We're talking about heat. Now, in science, heat isn't just about how hot something feels. Heat is specifically the transfer of thermal energy. And today, we're going on an investigation to figure out exactly how that transfer happens.
To really get this, we have to zoom in. I mean, way in. We're going to look at what's happening at the level of atoms and molecules, because that's where the story of thermal energy actually begins.
Okay, so every single thing, the air you're breathing, the chair you're sitting on, it's all made of tiny particles that are constantly moving. They're vibrating, they're jiggling, they're bumping into each other. Thermal energy is just the grand total of all that movement from every single particle in an object. The more particles you have and the faster they're all moving, the more thermal energy you've got. Simple as that.
So, what's temperature then? This is where it gets really interesting. Temperature isn't the total energy, it's the average energy of all those moving particles. When you stick a thermometer in something, it's basically taking a poll of how fast, on average, those particles are jiggling around. It tells you how energetic a typical particle is, not how much total energy is in the whole thing.
And this little difference leads to some pretty wild facts. Think about a huge ocean versus a steaming hot cup of tea. The tea obviously has a much higher temperature, right? Its particles are zooming around like crazy, on average. But the ocean, with its trillions and trillions of particles, actually has way more total thermal energy, even though its temperature is way lower. The key takeaway here is, a high temperature doesn't automatically mean high thermal energy. So, how does that thermal energy actually get from the fire to the poker? Well, it always moves from hotter things to colder things, and it travels along three main highways. First up, you've got conduction. That's heat transfer by direct touch. It's like a line of dominoes. One particle bumps its neighbor, which bumps the next one, and on and on. Then there's convection, which happens in fluids, like air and water. Warmer, less dense stuff rises, and the cooler, denser stuff sinks, creating this circulation that carries heat with it. And finally, there's radiation. This is pure energy, traveling as waves, like the heat you feel from the sun or a fire. It doesn't need to touch anything. It can even travel through the vacuum of space.
But here's the thing, it's not just that heat moves, it's how fast it moves. And understanding that speed is the real key to cracking our campfire mystery.
The big idea here is something called thermal conductivity. It's a fancy term, but all it means is how quickly a material can pass thermal energy along. Some materials are like superhighways for heat, and others are more like slow, bumpy country roads.
This basically splits materials into two groups. You have thermal conductors, which have a high conductivity. Things like metal. They transfer heat super fast. That's our metal poker. On the other side, you have thermal insulators with low conductivity, things like wood or plastic. They slow that heat transfer way down, and that's our wooden marshmallow stick. So mystery number one, solved. You've definitely felt this before, right? If you put a thermometer on a tile floor and a rug right next to it, they'll be the exact same temperature. But the tile feels way colder. Why? Because it's a better conductor. It's basically a heat thief, pulling that thermal energy away from your feet much faster than the insulating carpet does. That's what creates the feeling of cold. All right, so the poker versus stick part of the mystery is solved. But what about the heat you feel on your face when you're just sitting near the fire? That's radiation. And it turns out not all objects play by the same rules when it comes to radiation. We have all experienced this, for sure. It's a gorgeous sunny day, but if you're wearing a dark shirt, you feel like you are absolutely cooking. What's up with that? Well, the answer is all about how different surfaces deal with thermal radiation. Yeah, it turns out the speed that an object soaks up or gives off radiation isn't random. It depends on a few key things. Its temperature, its color, its texture, like is it rough or is it smooth, and how much of its surface is exposed to the world. And here's the rule of thumb. Dark, rough surfaces are amazing at absorbing thermal energy. That's your black t-shirt getting hot in the sun. But here's the twist. They're also excellent at emitting energy. A black object will both heat up faster in the sun and cool down faster in the dark. Smooth, Light-colored surfaces are the total opposite. They reflect most radiation, so they're bad at absorbing and bad at emitting.
So we've got conduction, we've got radiation, and everything is constantly giving and taking energy from everything else. This brings us to the final, and honestly the most important idea of all. The universe is always trying to find a balance. Okay, here it is, the big secret. Right now, as you're sitting there, you are both absorbing thermal radiation from the things around you, and you're emitting your own. Everything is. It is a constant two-way street of energy. What decides if something gets hotter or colder is simply the end result of that exchange.
The logic is actually super straightforward. If an object absorbs more energy than it gives off, what happens? Its temperature goes up. If it gives off or emits more energy than it takes in, its temperature goes down. And what happens when the amount of energy coming in is a perfect match for the amount going out?
Well, it reaches a state called thermal equilibrium. This is the balance point. The energy is still flowing, but the rates of absorption and emission are totally equal, so the object's temperature just stays constant.
And this explains something you see all the time. If you leave a cold drink and a hot coffee in a room and come back in the morning, the drink, the coffee, the table, the air, everything will all be the exact same temperature. They've all reached thermal equilibrium with the room.
So why does any of this matter? Because understanding these rules is how we control heat in the real world. It's how we design a thermos with a vacuum to stop conduction and a silver lining to stop radiation. It's how we engineer coolers, and how we understand that wearing layers of clothes keeps us warm by trapping air, which is a great insulator. So let's wrap this up with a little challenge for you. Using everything we've just covered, conductors, insulators, the rules of radiation, and the 3 ways heat moves, how would you design the perfect container to keep ice cream from melting on a blazing hot day? What materials would you use? What color should it be? Think about it. You now have the science to engineer the ultimate solution. Until next time, stay curious.